All right, so I think we can get started. Thanks everybody for coming to the Marine Science Seminar. I'm happy to introduce our guest speaker, Eric Chassignet from Florida State University. He is the director of the Center of Ocean Atmospheric Prediction Studies there. He's also a distinguished professor. His background, he got his PhD in physical oceanography from the University of Miami. He also did postdoctoral work at Woods Hole Oceanographic and the National Center for Atmospheric Research. He's had faculty positions at both the University of Miami and Florida State. He's active with teaching geophysical fluid dynamics, and he's advised more than 25 graduate students and has received funding for his research from just about every oceanographic agency that you can imagine. So today he's going to be talking to us about high resolution ocean modeling, and I hope our screens are not too pixelated that we can see the high resolution that he's going to be talking about, but please let's welcome Eric.
Well, thank you very much. And feel free to ask, if you have clarification, question, whatever. I don't mind being interrupted. So what I'll report is on experiments that we've been performing for the past few years, and that's work that I've done in very, very close collaboration with Xiaobao Xu, who used to be at USM before coming to Florida State. So first, I'd like to, a little bit of breakthrough that was now close to 25 years ago, is when we were able to run the first eddy permitting or eddy resolving North Atlantic simulation that showed a realistic Gulf Stream separation. And really, the big difference is that by working with a computer scientist, we were able to take advantage of the newly designed parallel computers and therefore increase the resolution. And that's really made a big difference. And then there was a couple of papers that were published a few years later after that. Well, now about 20 years later after these publications, those type of models are now global, and they are routinely used for ocean prediction, like the Mercator in Europe, the HICOM-based Gulfs at NRL, Blue in Australia, and so on. And soon now, we have actually now HICOM 3.5 is in place and operational. And then within the US Navy, you have the next steps are probabilistic ensemble forecast with 50 members using HICOM at 1/12th degree and NavGen at 37 kilometers, and then one deterministic configuration fully coupled, but with a 1/25th degree ocean models. In the meantime, the resolution has also increased in the configurations, global and basin, and we have a few examples going all the way to 1/50th degree, but those are extremely expensive, so they've been run only for a few years globally with the MIT GCM, and then you have regional Atlantic configuration run with a French NEMO model and with HICOM. I'll get back to HICOM. And then, 1/10th of a degree, how is it used within the climate community? And more, there is a lot of interest in trying to determine the impact of eddies in the coupled long-term climate integration, but it's also very demanding computer-wise, so there's not that many yet. But before going to fine resolution, let me bring up one question which is relevant for climate type of simulations is, beneficial is it to go from coarse on the order of 1 degree, which is a typical CMIP configuration, to global eddy resolving 1/10th of a degree. So as part of the CLIVAR Ocean Model Development Panel, 4 modeling groups configured the high resolution models with the same, very similar parameters to the coarse resolution, and all force using the same atmospheric forcing, which is GR55. and integrated for 60 years. The model that took place is HICOM, the hybrid coordination model that forms the base of the GOFs, the NRL GOFs. POP, that is the NCAR model, the German model, and WICOM is the Chinese model. So I'm not going to go into the detail. This paper was just published about a month ago. The reference is here at the bottom. But the take-home message is like the first slide I showed, is that the bias or the representation of the western boundary currents and equatorial currents, the ACC, everything has significantly improved when you increase the resolution, which is to be expected. But despite the fact that all these are improved, that doesn't mean that temperature and salinity in the three-dimensional structure are all improved everywhere. It depends. Some models are better in some location than others. So I refer you to that paper for that information. But let me go back to the improvement in, and especially in, focusing on the North Atlantic. So the high resolution experiments are here at the top, and the lower resolution at the bottom. And the main result is that when you have coarse resolution, the Gulf Stream overshoots in all simulation, and you show some, like you see in the HICOM, for example, some improvements in the separation. But another issue that is remained in some of the models is that the representation of the North Atlantic current in the corner here, that's the observations, the best estimate from the observation, is reasonably represented in some, and some others have the subpolar area that is way too big, and then the North Atlantic current and the extension of the Gulf Stream is way too zonal. So that still remains an issue. The other aspect is that the bottom three left are, of course, resolution, sea surface height variability, and without eddies, there is very low sea surface height variability compared to the observations that are on the right here. As soon as you increase resolution, you start to have a much better agreement with the observations. So that's one of the benefits of increasing resolution. But they all still underpredict the observed sea surface height variability and the eddy kinetic energy, especially in the interior. So what we argue is that there is still a need for further refinement of resolution or improvement in less dissipative numerics. So that brings me to the next step. Well, first, why there is an improvement when you go to 1/10 of a degree. It's because mostly the first balcony Rossby reduced deformation is resolved. So therefore you have more instabilities. And also, when argument has been put forward that the flow may exceed the critical Reynolds numbers, or in other words, they are more inertial, and therefore can, in the case of Gulf Stream, separate from the coast. But it's unclear. I mean, even some models at 1/10 of a degree can separate well, some do not. So there are many factors. And in a review, more than 10 years ago, we tried to identify all the factors that could play a role. So with Xiaobao, what we set out to do was to systematically investigate the impact of resolution. 1/12, which is, was routine, 1/25 used at the Navy, and then go all the way to 1/50 of a degree. We have some 100ths of a degree Gulf of Mexico, but I'm not going to talk about this here. So the main question is, what is the added value? What can we learn as we increase resolution? So the configuration we used is from -28 south to 80 north with closed boundaries, but relaxation to climatology, monthly climatology of the north and the south. And they are identical vertical stratification, and the topography, which is a big point, is the same topography in all simulation as we increase the resolution from 1/12 to 1/50 of a degree. What we do is we interpolate the 1/12 of a degree to the 1/50 of a degree. And then viscosity is changed as a function of grid spacing as we go from 1/12 to 1/25, and then we kept everything constant at 1/50 of a degree. And that's, it takes about 500,000 CPU hours per model year for the 1/50 degree, so they're quite expensive simulation. That's why you have only 3 groups in the world that are actually running this kind of configurations. So here is the evolution of the total kinetic energy for each of the simulation. As you go from 1/12 degree in red here, you double the resolution, but you decrease viscosity accordingly, you pretty much double the level of EKE, but at 1/50th of degree, which has a similar amount of viscosity, is similar to the 1/25th degree. The idea behind it is try to just isolate the impact of the resolution alone. So here's a movie a little bit just so we see what the 1/50th degree does. I mean, you see that in this case, you have a little deflection of the Charleston bomb, nice separation of the Gulf Stream, nice penetration in the interiors, eddies forming north and south. You can see also in the subpolar gyre and the Labrador Sea, some eddies being formed here. No special current eddies forming through loop current and so on. So that's just the speed, so the surface current speed. This translates into vorticity. And what you see, what is really special about this resolution is you start to resolve subgrid scale, sub-mesoscale eddies, which are really the tiny little features that you see here, and they vary seasonally. So in the spring, I'm sorry. So in this March, that's when the mixed layer becomes more unstable. You see a lot of eddies everywhere, little sub-mesoscale features. And as the summer and the mixed layer retreats, the instabilities diminish, and you start to see less and less of those sub-mesoscale features. So here's a zoom on the Gulf Stream. On the left is a vorticity again on the for the 1/12th degree, and you see how big, you see everywhere some mesoscale features. But now, as you get into the summer, you see that the eddies are bigger, and you don't have as many smaller scales. That's mixed layer instability not taking place. So the impact on the Gulf Stream is profound. I mean, as you go from 1/12 on the bottom left, that's a time mean sea surface height. You see a separation that kind of, the stream is not as tight, around here, and then it's much tighter, and as inertial gyres that is bigger. So if you compare all the simulation with our latest, one of the best observational estimate from the CNES group, the French Spatial Agency, and you see when you compare the observations to the 1/50th degree, you have a very good one-on-one agreement. The 1/12th degree, you have a good separation, but then the jet stops pretty much from penetrating the interior and becomes much more unstable. 1/25th degree is even worse. It cannot go past the New England seamounts, and you have a lot of recirculation taking place at south of Cape Hatteras. Yeah. So if we look, question? Okay. And so if we now look at the corresponding sea surface height variability on the top left is from based on the Aviso sea surface height variability for the past 20 years. By the way, I mean, the simulations were integrated for 20 years, and we show the time average over the last 5 years of the integration. So what you see is the 1/50th degree, that as far as the extension looks pretty good, but you have kind of a big blob, and it looks much bigger than the observations. 1/12th degree is confined west of the New England seamount, same thing for the 1/25th degree. So at least you appear to have a decent match between the two, but there is a question as why is the variability greater in the 1/50th degree. So we'll get back to this in a second. But first, let's look at the impact of, we're going to look at a cross-section here on this line, look at the impact of the sea surface height variability on the interior. So that's based on measurements that were taken at 55 West by Richardson. And it shows that the mean velocity the Gulf Stream of the surface extends to about 1,000 meters, and with some signal all the way in the vertical. If you look at the 1/12 of a degree, it's mostly confined to the surface, and you don't have any penetration in the interior, or not, not combined. They're disconnected between the two flow here. It starts to get better as you go 1/25 a degree, and it's more pronounced at 1/50 a degree. But I think the better figure that truly represent how well the variability of the surface propagates into the interior is by looking at the eddy kinetic energy. And that's on the left from the measurements, where you see that it penetrates all the way to the interior. There are none in the 1/12 a degree. Okay? And you start to see some taking place in the 1/25, but it's only when you get to 1/50 degree that you start to have a good agreement with the observation. So going to 1/50 degree makes a big difference as far as the propagation of eddy kinetic energy into the interior. So going back to the surface EKE, so on the left is based on a VISO, so we switch from this surface height variability to surface EKE. This is the total, including H geostrophic motion. This is only based on geostrophic velocity derived from the sea surface height. So as mentioned before, 1/12, 1/25 do not agree well with the observations, and the 1/50 look better, but still is pretty bigger and larger. So we set out to answer the question, why is the model surface EKE in the Gulf Stream higher than altimetry? So is it just due to contributions that are ageostrophic, or simply because the spatial and temporal averaging in the observations reduces the amount of EKE? So this is computing the same way as it's done in a VISO, meaning we compute the EKE using geostrophic velocity, and at quick glance, it doesn't make that much of a difference. And if we do the difference between the two, you see here on the bottom left, you have a little bit of a background in yellow everywhere, and that's due to the Ekman flow at the surface that is not taken into account when you compute the geostrophy. And the other part is due to the fact that you have curvature when you compute the so you have a deviation from geostrophy just due to the fact that you have a gradient wind balance in the eddies or in the meanders of the stream. So the bottom line is that there is ageostrophic effects, but they do not really matter that much. So what we did is we started to look at what is the impact of the subsampling that takes place in a VISO. And for this, we looked at the sea surface height spectra in the North Atlantic. So we picked, this box in red and looked at the various representations. So you have more and more information as you increase the resolution to 1/50 degree, which is about 1.5 kilometers in this region. And the slope doesn't really change much between 50 and 250 kilometers. It's about -5 for all simulations. So that's in good agreement with QG turbulence theory. And it's also in good agreement with some observations as well as both from in situ and from satellites. There is a seasonal dependence, but that seasonal dependence is mostly when it's in the smaller scales, like I showed before, and showing the vorticity movies. So what we did is in red is within that box is the power spectra of the whole for the whole field. Then we project on the aviso grid. And automatically you start to lose, because it's coarser than the 1/50 degree, you start to lose information below that scale. Then we perform a 10-day average, which is equivalent to what the satellite does, as 150 kilometer bandpass, and that's in blue and cyan there. And then when we combine the two in purple, you see that the power spectra becomes very close to what you would get if you take only the satellite data only. So what this indicates is that the subsampling in time and space of the satellite sea surface height anomaly matter. So what we did here is the total EKE. Now, if you add 150 kilometer bandpass, that's what you get, and that's what you get when you do a 10-day average as well. That subsampling the numerical model in a similar fashion to a VISO gives you something that is much closer to each other. You still have a little bit of extra EK here, and we'll get back to this in detail a little bit later. To summarize, I mean, that's pretty much, a paper that Xiaobao and I published about 3 years ago. That increasing to 1/50th degree is, leads to a significant improvement in western boundary current pathways. And, we argue that, truly resolving the sub-mesoscale is another regime shift, like we observed, 20 plus years ago when we went to 1/10th of a degree. So the level of EKE, the separation, everything becomes much more comparable to these. But like I pointed out, the model, the sea surface height variability, or EKE, is wider near the New England seamount chain in 1/50th degree. So this suggests that interaction with topography may be overemphasized in that specific configuration. So we embarked into a series of sensitivity studies. And the first one that we did was relax the bathymetry assumption. What we did is when we integrated 1/50th degree, because we didn't want to change much except from the horizontal resolution, we kept the same bathymetry in the 1/12th degree and the 1/50th degree. So what Xiaobao did was to update the bathymetry and using the 2019 JEPCO 1/52nd resolution dataset. And here's what we get. You see that now everything is also projected on the VISO grid with the same time average. On the bottom left is the sea surface height variability, and you see that you have a lot around the New England seamounts. But just switching from one bathymetry to the next, everything else is kept identical. There's nothing else changed. You see how drastic of a change it is, and suddenly what you see is a much narrower amount of EKE, but also this little dog leg to the northeast there is also visible in the simulation. So you have a really big change, just changing the bathymetry. Has an impact also on the mean sea surface height. If you look carefully in the original experiment, you see it's start to be quite broad, the sea surface height, meaning that you have a lot more variability in this location here when compared to the observations. But as soon as you change the bathymetry, the jet is much tighter, and then you see the deflection to the northeast taking place, which is argued is induced by the bathymetry. So if we look a little more carefully at the difference in bathymetry underneath the Gulf Stream, so the time mean flow sea surface height is represented in the light gray contours, and you see that they are much sharper, but also they're more isolated in New England seamounts than here. And at the bottom, you see the difference. You see the red is a positive versus negative in blue. And so you see you have kind of a sharper definition of the New England seamount. If you take a cross section against the New England seamount, and you see with the high bathymetries in blue versus red for the old bathymetry, and mostly what you have is the seamounts are just a few hundred meters, about 500 meters taller, and they are more sharply defined, meaning that you have a separation between these features. So what we're inclined to think at the present time, and we're still investigating this, is that the jet is seeing this to seamount as one or as a bigger feature, therefore having a stronger impact on the surface flow and becoming deflected and having more instability. So that's where we stand as far as the explanation here. So we think that these narrower and higher topographic features have a significant impact. We're not 100% yet clear, but we're looking at literature and some idealized experiments, but wider topography will lead to larger jet displacement. So these reduced instabilities lead to a tighter Gulf Stream. But I think, it was unexpected. Just refining, the resolution, and it doesn't look that much, has a profound impact on the Gulf Stream pathway. So that's one of the messages from this set of experiments. The other thing I wanted to bring up that we've been working for the past year or so, a couple of years, is that there is another discrepancy in the base simulation. If you look, so now if we go back to the sea surface height spectra, and we're interested in the mesoscale range from 70 to 250, we look at the slope. And that's a common measure of, is it QG turbulence or, just of the flow. And that's what, based on satellites, Zoedal and FSU and more recently Dufour et al., they've produced global maps of the slope between 70 and 250 kilometers. And if we focus here on the Atlantic, you see that they show something around -5 around the Gulf Stream, which is what we obtained. But then it decreased all the way to on the order of -1 in the equatorial region. If we do the same in our model, you see that it's 4.9, 4.8, but it doesn't really change that much with latitude. If I take this one, you have 4.5, maybe a small decrease, but still 4.5 at the equator remains. There's no latitudinal dependence like you see in the observation. So why is that? So, those that were all computed daily average, and internal tides have been shown to have a significant impact on the wave number spectra. By the way, our numerical results were not unique. I mean, many other published the same thing. So what we set out to do was to look at what is the impact of tidal forcing on the wave number spectra. So here what you see, I hope you can see the movie, is a spin up. I mean, this is 1/25 with and without tides. 1/50 is the same thing. And what you look at is, on the left, it doesn't appear to be moving because it's every hour, but you see the impact of the tides on the surface velocity field. So mostly, where you have a lot of large tidal signals is where you see velocities changing rapidly. So this is a spin up. So it takes, a few days before the tides and the velocities start to show up and surfacing. So it does have an impact on surface speed, but not that much. Now, if we look at this is a spin up again. So initially the model is pretty, doesn't change much, and then the tides come in. You start to see them rolling through the domain. And the main point here is you start to see some surface signature associated with topographic features right here in the interior. And that's what one of the things that we're going to start to look at. Okay. All right, so we did another series of experiments. And so you have the base experiments. We do tidal forcing with and without wave drag, and then add high resolution bathymetry, and then high frequency hourly atmospheric forcing. So that's a little bit all the series of experiments that we did with that configuration. And what we used to show the impact of tides is to look at the steric sea surface height RMS daily, and then we take a monthly average. That's what we show here. So if you don't have any tides on the left, with or with high resolution bathymetry, you see that there is almost, there is no high frequency motion in the interior. They're only associated with the western boundary currents, and it's very quiet in the interior. As soon as you start to add tides, the internal waves start to have a very strong surface signature, and they appear around the Azores, around where you have the Cape Verde Islands, the Amazons. And one thing to note is that once you start to add also the high resolution bathymetry, I mean, you do have a little bit of a hint here of the Georges Bank, but you start to have a much bigger signal of here. Also, the other place where the tides appear is off Gibraltar. So what can be done is just to show the impact, is that the in blue and red here at the bottom is without the tides, and you see that the increase in steric sea surface height RMS is quite strong throughout the whole width of the domain, and with a stronger point due to the tides of the Med in the Gibraltar. And if you do the same thing for the equatorial band, it's more in the region of the Amazon here, where you see very strong signal. You can do the same thing for, instead of a monthly average, for the annual, and that really maybe more cleanly shows the impact of Georges Bank, the Azores, and Brazil. So the high resolution bathymetry does matter here. So the next step, what we did is, what is the impact in the equatorial region? I mean, before we had a slope of -4, -5. So let's see what we get in that region. So what we take is we do 4 10 by 10 degree box, like in the observation, and then average over these 20 by 20 box. So first, without tides, that's in red. You see the slope is steep, -4, 4.5. On the right is the spectra computed using the 2D fields. And what you see is that you have 2 peaks that shows associated with a different tidal range. But then what we did is to start to see, okay, that doesn't look like much observation. Is it possible then the subsampling by the satellites matter? So what Chabal did was subsample the sea surface height along the tracks, like in the observation, and then recomputed the spectra, and that's what you see in blue. And so there is a significant aliasing taking place when you actually subsample the fields, like in the altimetry does. And in this case, you get a much smoother fields. So now if I go back to the left panel, where you see the blue one, which is done exactly like the altimetry, now we can compare that to the observations. And the most recent estimate of Dufault et al. Is in continuous gray, which is right here, which is this one. And then Zhu et al. Did with and without filter the noise. They made an attempt to try to remove the noise from the altimetry. So without both Dufault and the top black line from Zhu et al. Are not filtered, and you see that you have noise here. And when they filter for the noise, here's what they get. And you see how closely it matches the model. So I think we're pretty confident to state that the flattening of the slope that takes place at the equator is due to internal tide signature. Here is the summary of this. So this is Zuidel, the slope. So in blue, it's on the order 1 to 2 around the equator, about 5. So on the left here is without tides, and where you see very little change north and south. And when we have the tides and subsample, I mean, all those are subsampled along the altimetry tract, you start to see that you have a very good match between the two, between the observation and the numerical simulation with tides. So in summary, I would say that, you know, there is another possible regime shift at 1/50th degree when we start to, you know, resolve the submesoscale, and there's a significant improvement in Gulf Stream representation. But high resolution bathymetry has a much more profound impact on the Gulf Stream pathway than one would have a priori anticipated, meaning that, you know, a more accurate resolution leads to a better Gulf Stream pathway and EKE. And the internal tides significantly flatten the spectra in the equatorial region, and that's in agreement with the observations, something that we wanted to answer for a long time. So thank you very much, and I'll take questions now.
Okay, thanks very much, Eric. I will try to help manage the questions, so you can either raise your hand or type in the chat, or just start talking. It looks like Martin has a question.
Yeah, thank you, Eric. It was a very nice talk. Can you take us back to the slide where you showed the vorticity and you showed all these fine, these small submesoscales? I actually have two questions related to that slide. So I wondered if you also see that sort of fine scales at depth, right? You see these submesoscales in the high resolution simulation really at the surface, but do you see these features also at depth, or is it mostly concentrated to the region above the thermocline?
Well, there are mixed layer instabilities, so they are mostly present in the mixed layer. But it's a good point to see. We looked in a recent paper with Joe Lacaze, we looked at the vertical coherence of the eddies, but we did not look at to see if the submesoscale features also project into the interior. So, I mean, you have a bigger penetration of EKE, but is it due because you have a better extension to the Gulf Stream and a better representation of mesoscale activity, or is it also due to an increase in mesoscale activity that project into the deep ocean? That's a good question. I don't have the answer.
Right, and actually, and my second question related to that slide where you show the penetration of the EKE, and that's interesting because you don't change the vertical resolution, you only change the horizontal resolution. So what kind of processes then drive that penetration if you just increase the horizontal resolution?
Okay, so it's I mean, the only way you transfer kinetic energy to the deep ocean is through pumping, through pressure, you know, displacement of interface. So when you move the interface up and down, you start to generate motion in the deep ocean. And that's what the eddies at the surface do. So the fact that you have a you know, better penetration of the Gulf Stream, you see stops here, and then it becomes much less coherent afterward. When you have a lot of eddies, you know, once passing the endurance amount, you start to have more energy that is pumped downward by interface displacement as the eddies move around.
Okay, yeah, so it's sort of similar that you resolve more, say, more horizontal wavelengths in a high resolution, so you create more eddy wave features that start pumping things into the vertical. Okay, yeah.
Correct, yeah.
Yeah, nice. Thank you.
Stephen? I think you've got to unmute.
Thank you. Yeah, thanks a lot for the seminar. I was wondering, you focused on the open Atlantic, but have you also looked at the loop current separation problem, and do you see the seasonality that's being seen in the altimeter?
So, yeah, so I could, give a full talk on the Gulf of Mexico, because we spent a lot of time looking at various, we have a regional Gulf of Mexico model that we have run all the way to 100th of a degree. We have run for 54 years. One paper by Dmitry Dukovskoy was published a few years back, and then there's one in preparation right now where we also have climatological boundary conditions that were changed to more realistic. We see a little bit of seasonal dependence in the simulation. Yes, we do a little bit. I mean, we can maybe pursue this conversation offline, because it's one thing that we found very surprising is that how sensitive the Gulf of Mexico loop current formation is to bottom drag formulation. And that's in the context of comparison with MOM6, is another numerical model. And we found that if you reduce the bottom drag, especially in the interior of the Gulf of Mexico, you shut down the loop current eddy formation. It behaves very differently. So that was very surprising results that we do not fully yet understand. I mean, it does change the bioclinic structure of the flow, but to have such an impact is so we're onto something, but we're not sure exactly what.
Okay, I had a question. I'm sorry, it's more of an observational question. But the Aviso satellite sea surface height is basically making the measurement at a lower resolution than you have in your model.
Correct.
So is there any other type of measurement that could match your resolution? Because it would be nice to have some way to verify rather than just having to subsample.
Well, there is a new satellite mission SWAT that is going to be launched in a couple of years from now. That it's a white swath and would truly resolve the mesoscale.
Okay.
So we're going to get some better data, but no, I'm not aware of anything else that. I mean, we try to use everything we can to compare the model to them. It's hard to find observation that's sufficiently dense in spatial coverage and time to compare to the model.
Right. But yeah, I understand looking at the impact on the deep ocean was a nice way to check.
So we also, I didn't present here, but in the paper, we also compare at 750 and 1,000 meters. And 1,000 meters, we use some estimate from Argo, but it's also very primitive and based on, at the end, they end up averaging all the Argo measurements on a 1 degree grid. So it's pretty coarse.
Okay, I think Miguel Solano had his hand up next.
Yeah, hi, Eric. Thanks for the presentation. It was pretty insightful. My question is that as you increase the resolution, so it's like a twofold question. So one is, as you increase the model resolution, a lot of the basis for the turbulence parametrization that are based on QG theory start to break down at the sub-mesoscale, right? So how do the tuning parameters or the parametrizations change in your models as you increase and go to higher resolutions? And then the second follow-up question is, how does the bottom drag parametrization change with the bathymetry? So you show that the bathymetry, the high resolution bathymetry, had a significant impact on the EKE fields. So how does the bottom drag parameterization change if you change the bathymetry, for example?
Okay. So to answer your first question, going to 1/25th to 1/50th degree, nothing has changed, and we kept the viscosity the same. If we did give it a try at decreasing the viscosity, but the model becomes unstable. So that's something we need to work on and refine that. The other thing that I didn't mention that I could spend some time is the atmospheric forcing. In this particular case, we are using absolute wind, meaning that the wind stress is computed assuming, not taking into account the shear between the atmospheric winds and the ocean currents. When you do that, you reduce the surface EKE by about 30%. So that's one of the next steps that we want to do, is to be able to take that into account and reduce the viscosity to see what is the impact on the Atlantic simulation. So the fact that you have prescribed atmosphere, an atmosphere that is coarse compared to the ocean, I mean, it's about, what's, if I recall correctly, about 30 kilometers versus 1 kilometer in the ocean. So you have, and the atmosphere is not allowed to respond to the eddies or submetascale eddies. So it's a big question that we are after. So it's a little bit of a side answer to your question, but it's a very important one. The other one, the bottom drag is simple quadratic. So we did not change the formulation, and it's applied to the bottom 10 meters of the. So yes, I mean, in this case, the depth at which the bottom drag is applied, or around the seamount, is going to change a little bit. It's a good question, but I don't think it makes that much of a difference. But maybe it's a good question for us to think about. The fact that the bottom drag is going to be at different locations that may affect the vertical shear.
Thank you.
Did you have a follow-up, Stephen?
No, I didn't. I'm sorry.
Oh, okay. Do we have any other questions?
Yeah, I have a follow-up.
Oh, okay. Go ahead, Martin.
So we're working on you with Miguel and you on this TFO project, and so we're looking into sort of doubling the effect of the vertical resolution, right?
Correct.
Which is still sort of unknown. But do you have an idea what will happen to the Gulf Stream if you double the vertical resolution?
So yeah, I don't think much would happen. That's my guess. Shabbat's run some simulation at 1/12th degree with 64 layers instead of the 32, and there was not that much of a difference between the two simulations. 32, I think in a series of paper, what we did is we compared this 1/50th degree resolution to the 1/60th degree NEMO model, which is a French model, and they have 300 levels in the vertical, and all the energy transfers, I mean, all the statistics that we could do between the two models did not show a big difference. So the fact that, at least in the Gulf Stream region, 32 layers is enough to resolve up to I think the 5th Rossby radius of deformation. So the first 5 bioclinic modes. And so if we add more layers, and the fact that it is a layered model allows us to keep the water mass discretization, doesn't change that much. I mean, you still are able to keep track of the vertical discretization well as the interface move, when a fixed coordinate model would have to have at least twice as many levels just to keep track of those density displacement. So that's one of the reasons we've been pushing isopycnol-based models. And so I don't think you're not going to necessarily resolve the water mass that much better and therefore have a profound impact. Maybe I'm wrong, but that's my, since you're asking what I think, I don't think it's going to change much.
Right. Yeah, I think based on the internal wave studies that we have done, is that if you double the horizontal resolution of your model, you get twice the number of modes. Well, you can easily resolve like 10 modes in the vertical, but clearly
Right.
the horizontal resolution is the limiting factor here.
Yes.
Yeah.
If I can add comments, one.
Or Xiaobao, introduce yourself. So
Oh, I'm sorry. I'm Xiaobao. Yeah.
Xiaobao Xu, co-author of this work.
So we did, as Eric mentioned, we did at 112-degree 32 layer and also 64 layer, and the results are very, very consistent. I mean, pretty much consistent with each other. This one small difference is that when you have more vertical layers, the diapycnol mixing can change a little bit, and that's the only major, change I can anticipate in terms of large scale circulation. Yeah. So we do want to run this configuration at a higher resolution, but it's just very computationally expensive. That's yeah.
I had one more question relating to the higher resolution bathymetry. I'm sorry if this is a naive question, but does that add any computational cost to the computation?
No.
So everyone should do that if they can, right? It makes it more realistic.
Yeah, the only reason we didn't do it is because it was we were trying to do a convergence experiment, trying because if you change too many things as you increase resolution, then you don't know which factor matters. And I personally didn't think that there was the difference between 1/12 degree, which is about a 6 kilometer, about 6 kilometer versus 1.5 kilometer. In the bathymetry, would make a difference. I mean, that was completely out of the blue. The main reason we did that was to see if it had an impact on the generation of internal tides, and the surprising result was on the gulf stream. I mean, it has an impact on the tide, on the strengths of the tides and where they are generated and everything, but it's. That result is, it's amazing how better the Gulf Stream is just by changing the bathymetry. And it's not, you refine from 6 to 1 kilometer. It's not a big change. But it's first order change, which really is maybe one of the take-home message of this work.
Yes.
But still, you have the internal tide beam from George's Bank.
Well, no,
and then the question is, okay, how much? Probably the energy flux has increased as well. The question is how much. And the other question is there any coupling between the internal tides and the mesoscales? I mean, there should be, of course, some nonlinear advection between the two.
No, but the simulation here is without tides. The one I'm
okay, all right, okay.
Resolution matters. I mean, the tides are going to change in that region, but this is no tides, and the only difference is the bathymetry.
Right. And could there be a cumulative effect because the Gulf Stream is sort of traveling along the East Coast shelf, and so you better also resolve features along that entire shelf. So could there be a cumulative effect of, can you really pinpoint it to that island ridge?
Well, there's not much. Yeah, there's not much of a difference before. Well, you're right. I mean, it's a little bit tight. It's a good question. It's a little bit tighter here than here. One thing that we're doing right now is looking at the vertical sections before and after and on the ridge to see if the EKE and the penetration of the Gulf Stream differ. Yeah. Well, my suspicion is that the fact that you have more radioactivity around here propagates upstream, but that's a good question to look into. Yeah, I don't think so, because I could, I don't have a map. I mean, if you look at this map here a little bit, but if there's almost very little, you see the difference is minuscule ahead. And maybe prior to the separation, but in the abyssal plain here before the New England seamount, there's not much. So, but again, that's a good, when you add, actually, Shabao, I mean, the paper that we wrote with Joe Lacaze, when you add rugosity, you add bumps at the bottom, you actually stabilize, you can stabilize the Gulf Stream. So, there's something into it there. Thank you, Martin. We'll think about it. Maybe the fact that you have a smaller scale features may help stabilize the Gulf Stream ahead. Yep.
Yeah, there's also a little bit difference in the upstream near 68 degree. The path is a little bit different.
Yeah,
If you zoom into it, you will see, but
yeah, it's tighter here. So
yeah, a little
bit. Either it could be eddies propagating westward,
so
or the fact that the stream itself is more stable before hitting the ship. Okay.
So I think what are we doing to look at the vertical section at that upstream location and downstream location might give us some indications.
Okay, any final questions? Thank you so much for doing this, Eric and Javo. It was really nice to see this talk. And if anybody wants to follow up with Eric, I'm sure you could reach out to him. And it was great to hear more about your research today. So thanks, everybody.
Well, thank you for joining.
Thank you.
Okay.
Thanks, Eric.
Thank you for all the comments. That's very useful. Have a great day.
Bye-bye.
Thanks. Bye.